the fundamental theorem of calculus part 1, or we use the short term as FTC part 1. There are two parts, so we're going to start with the first one. For the function f that is continuous on the closed interval, the area function is defined by the a of x as a definite integral from point a to the point x, a as a lower limit, x as the upper limit, or a is a left bound, and x is any point between a and b where f is continuous on the closed interval. And from the previous example, we can see the relationship of the area function and the integrand as a derivative of the area function, or the derivative of the definite integral is the function f of x, or the integrand, the function f, insert the t variable as a variable of integration. We're going to use the x as x, the upper limit, as the variable of the result of the derivative of the a. Another way we can say that the area function is an antiderivative of the function f. Example, evaluate derivatives of definite integrals using the fundamental theorem of calculus part 1. Part A, we find the derivative, or d by dx, of the definite integral from 0 to the upper limit x, and the function is e to the power t. Let's make the note. The f of t is e to the t. And the definite integral, the derivative of the definite integral, or the fundamental theorem of calculus part 1 is stated as d by dx integral from the real number a to the unknown x of the function or the integrand f of t with respect to t equals f of x. What we're gonna put into this format is the lower limit has to be the real number. The d by dx, or the independent variable, has to be the same as the upper limit. Then we use this x notation to replace the t for the integrand function to become f of x. So the x will be placed into the position of the t. For part A, the example part A, we already have the constant as a lower limit, and the derivative with respect to x, the upper limit is x, so we can apply the fundamental theorem of calculus part 1 directly. As f of t is e to the t, the result of this will return as f of x. And since f of t is e to the t, so f of x is e to the x as a result of the derivative of the definite integral from 0 to x of e to the t with respect to t. For part B, we find the derivative of the definite integral from x to 1 of the square root of t to the fourth plus 1 with respect to t. For the fundamental theorem of calculus part 1, the lower limit must be the constant. The upper limit must be the same variable as the, the independent variable as you find the derivative. And for part B problem, the position of the lower limit and upper limit are not in the appropriate location. So we are going to rearrange it using the property. And this will become the integral from 1 to x instead. But when you swap the lower limit and upper limit, you're going to apply the negative sign to the definite integral. And now we can treat negative 1 as a constant multiple. And this will become negative of the derivative with respect to x of the integral, or the definite integral from 1 to x of the square root t to the fourth plus 1 with respect to t. For this situation, we already have x and x matching the pattern, and the function f of t for our case is the square root of t to the fourth plus 1. So then, after apply the fundamental theorem of calculus part 1, we get negative of the function of the x instead. Then get our final result as negative square root of x to the fourth plus 1. The next part, we find the derivative of the definite integral from 5 to x to the third of the integrand 1 over t plus 2. Let's make the note on the side here. The f of t is 1 over t plus 2. And we call the FTC part 1, which is the derivative with respect to x, the integral from the constant a to the variable x of the function of t with respect to t equals f of x. That means x here and x here have to match, or the upper limit and the variable as the independent variable must be the same. So then we can replace it over here. For our part C, we have the upper limit as a variable, but it's not just x, it's the function of the x, where the lower limit is okay. So we do not have to apply the other property. But we're gonna need some other property to adjust into the form that fits with the fundamental theorem of calculus part 1 in order to apply it. So we see x to the third power as a function of the x. We name it as um, the unknown u. So this case, u equals x to the third. If we rewrite this as d by dx, the definite integral from 5 to u of 1 over t plus 2 with respect to t, we have the upper limit as a u. Now we're going to make the dx here into the term of du. We're going to apply the chain rule. We call the chain rule. When you find the derivative of y with respect to x, and y is the function of the u, we can do that as dy by du multiplied by du by dx. So in our case, the u is x to the third power. Then this case, the d by dx notation, we use the chain rule formula to make it as an equivalent form. So d by dx is the same as d by du of the definite integral multiplied by du by dx. So now fill in the quantity here as a definite integral 5 to u of 1 over t plus 2 with respect to t. The first part, it matches with the fundamental theorem of calculus part 1 because the lower limit is number, the upper limit is the variable u, which is the same as the du for the derivative operator here. It's good to go. But the second part that what we have to work on, what is the du dx? From the note that we set aside, since u is x to the third, so then du by dx is 3x to the second. Now what we're going to replace into the du dx in the problem. Now, the first part, we can apply the fundamental theorem of calculus part 1 to be the function of the variable u and then multiply by 3x squared. And next, just complete the problem by substituting u with the x to the third to have 1 over u plus 2 multiplied by 3x squared, where u is x to the third. Then we get x to the third plus 2 multiplied by 3x squared, or 3x squared over x to the third plus 2 as the result.